Right, we use the empirical rule when we have a data set that is mound-shaped and symmetrical. It gives us an approximation for the potential data points between given z-scores. Now they're only going to be integers, so it's going to matter. We can't really use values of, say, 1.1, 1.2 and that sort of thing. For the empirical rule, we will have other means to do so with those values later on. But these are approximations. So if you note here, approximately 68% of the measurements will have a z-score between -1 and 1. So that is one standard deviation below the mean and one standard deviation above the mean. So in that range we should see about 68%. That doesn't mean we're going to get exactly 68%, that's just an approximation. Could certainly be off. Also, we're going to see 95% or thereabouts between -2 and 2. So 2 standard deviations below the mean and 2 standard deviations above the mean. And finally, almost all of the data will fall within 3 standard deviations of the mean, or about 99.7%. This is what the mound-shaped distribution looks like. So in the center we have the mean mu, and you notice these lines here, mu plus sigma, so 1 standard deviation above, which is a z-score of 1, 1 standard deviation below, which is a z-score of -1. So within 1 standard deviation we see 68% of the data fall there or thereabouts. We can further determine that there's 34% between a z-score of 0, which is right at the mean, and 1, and 0 and -1, because it's symmetrical. Anytime you're dealing with a distribution that basically is a mirror image, we're going to have the same amount on either side. So 68 divided by 2 is 34. Now our mean plus 2 standard deviations is a z-score of 2 over here, and this is a z-score of -2. We will see approximately 95% of the data fall within this area. So that means there should be 47.5% on either side, from mu to mu plus 2 sigma, 47.5, and from mu to mu minus 2 sigma, 47.5. Since we know that there's 34% between a z-score of 0 and a z-score of 1, 47.5 minus 34 gives us a 13.5% that will fall between a z-score of +1 and +2. So mu plus 1 sigma and a mu plus 2 sigma. And finally, for 99.7% of the data within 3 standard deviations, we will see that leaves out of 100% 0.3%, so 0.15% above it, 0.15% below it, and we can find this value out using simple subtraction. So this is the key that we're going to use when dealing with empirical rule. Now, if I give you a question, or if your computer gives you a question based upon approximations using a mound-shaped symmetrical distribution, you're going to use the empirical rule, and it's only going to help you if the actual values come out to be something along the lines of an integer. So exactly 1 standard deviation below or above, 2 below or above, or 3 below or above is all that is really going to help. Now, Chebyshev is more of a very general, conservative approach to determine the least amount of data between any two different standard deviations. Now this works for different values other than just the integers. So in fact it doesn't work at all for an integer of 1. If we use a number standard deviation for 1 standard deviation away, make k1, we have 1 over 1 squared, which is 1, so that gives us 0. So it doesn't give us any reasonable information. But for any value of the standard deviation that is above 1, we're going to use this formula. So for example, if we used k to be 2, so exactly 2 standard deviations above or below, what would happen would be 1 minus 1 over 4, which is 3/4. So about 75% of the data must, at least that much, must fall between z-scores of -1 and 1. If we had 2 standard deviations, that's going to be, excuse me, 3 standard deviations, that's going to be 1 over 9, so at least 8/9, or it's about 88.8%, something along those lines, will fall within 3 standard deviations. And again, that's at least. These are bare minimums. Typically you'll have much more than that. Now an example for our empirical rule. This question states that at one university, the students are given z-scores at the end of each semester rather than the traditional GPAs. The mean and standard deviation of all students' cumulative GPAs on which z-scores are based are 2.7 and 0.5 respectively. That means 2.7 is the mean and 0.5 is the standard deviation. And the distribution of grades is mound-shaped and symmetrical. So we know that we're going to use the empirical rule. So just a regular old z-score question. First of all, what was the GPA of a student who had a z-score of negative 2.5? Negative 2.5 isn't anything we can use the empirical rule on, but we can calculate the GPA using our z-score formula. So let's write down the information that we have. So the mean is 2.7, the standard deviation is 0.5. So that's what we know about the distribution here. Now our first question is we're looking for the x value, or one student's GPA, when the z is negative 2.5. So our formula is the z is equal to our value of x minus the mean over sigma. So we know this value to be negative 2.5. We don't know x, we're trying to solve for x. The mu is equal to 2.7, so we subtract 2.7, excuse me. And we're going to divide by 0.5. Now we're going to just do the little math here. So we multiply each side of the equation by 0.5 to remove this from the denominator. Negative 2.5 times 0.5 is negative 1.25. And that equals x minus 2.7. And when I add 2.7 to each side, that means my x will be equal to 1.45. So the school lists the z-score as negative 2.5, and that correlates to a GPA of 1.45. So that was the first of the questions. Second question, it's an approximation, so approximate what percent of students had GPAs lower than 2.2. Well, this we're going to have to try to actually determine what the z-score is. So for 2.2, we're looking for the z. Now 2.2 is our x here. And that's actually going to be minus, not equals. So minus 2.7 over 0.5. So this is negative 0.5 over 0.5, which is negative 1. So we're going to have a z-score of negative 1, and according to the question, we want the approximate percentage of students that had a GPA lower than 2.2, so that's lower than one standard deviation below. So a z-score of negative 1 falls here. Let's see if we can do this here. Thereabouts. And we're looking for the area over here. This is what we're looking for. We're looking for the area in the red over here. So we're looking for the percent below negative 1. Alright, so knowing what we know about the empirical rule, we know that between negative 1 and 1 we have about 68%. So 68% between negative 1 and 1. That leaves 32% left over. And that is equally distributed above and below. So this area here is going to be about about 16%. Half of that is what we want. That's that's about 16%. Again, 32% left over, which means 16% on one side, and 16% will actually be above the z-score of 1. And then the third problem, we're looking for the threshold for the top 16% and the top 2.5% of GPAs. Well, as we discussed, 1 will be the threshold, will be the z-score threshold for the upper 16%. If negative 1's the lower threshold for the bottom 16, 1 will be for the top 16. So we're looking at z of 1 for the top 16%. And then we're looking for the top 2.5%. So if there's 2.5% on one side and 2.5% on the other side, that's 5%. That leaves 95% in between, and our empirical rule is 95% within 2 standard deviations. So in this case, we're going to be looking at this value here, there and up. So we want the value at 1 and 2. So z is 2 for that. So for the top 2.5%, we knew z equals 2. Now, the question's actually looking for the GPAs, so we're going to use our z-score like this and calculate each one of them. So we'll use a 1 first and then 2. We multiply through, we get 0.5. And when we add 2.7 each side, we're going to have 3.2. So that's the value that we're going to use for one standard deviation, and the threshold for the top 16%. And for the top 2.5%, we use a z-score of 2. Same formula. And when we do the multiplication here, we're looking at 1. And finally, x here equals 3.7. So there's some different examples and different ways that you can use the empirical rule to determine either values of x or percentages or whatever it is you need.